Hello class, welcome to the next lesson in Eureka Math, 8th grade. We're in Module 4, getting ready to do Lesson 24 today that I'm calling Systems of Equations. Systems of Equations, and that is on pages 295 through 295 through 306 of your Module 4 workbook. Make sure you have that book out with you. Make sure you have those pages. Make sure you have your pages for your notes and all the other materials you might need for math today. Make sure they're close at hand. And as a reminder, before we start the lesson, you're in control of the speed of this lesson. If I'm going a little bit too fast, you can always pause the video to catch up on your notes, or you can go back and re-watch something that you might have missed or to get more clarification on things. If you understand what I'm doing, you're always allowed to also work ahead of me and then go back and watch the video again to check your answers. Remember, you're in control. Use the power of the pause, use the power of the rewind. Use the power of all the tools you have so that you can succeed. Do whatever it takes for you to succeed. But let's get to the lesson today. We're going to start, like we always do, with vocabulary. And today we have two vocabulary terms: system of equations and solution to a system of equations. Now, a system of equations really just means two or more equations. Two or more, in this case, linear equations that are connected to the same situation, that are related to the same situation. So these are two different equations that talk about the same thing that's happening. Two equations that talk about the same thing. So there are two different equations, but it's the same situation. Another word for systems of equations is simultaneous equations. So you might see both in your book. I grew up with system of equations. I probably won't use simultaneous equations too often, but just so you know, they are the same thing. The next word is the solution to a system of equations. So if we have two equations that talk about the same thing, how do we solve them? Well, I'm going to show you how we solve them, but when we have a solution, the solution is actually a set of coordinates, x comma y, that make both equations true. So a solution to a system is coordinates that work with both of them. The coordinates have to make both equations true, or it is not a solution to the system. A solution to the system makes all equations in the system true. So that's what we're dealing with today. We're talking about a system of equations, two different equations, and how to solve them. So let's summarize that. Today, we will use two different equations connected to the same problem to solve the problem. Two equations connected to the same problem to solve the problem. That's what we're doing today. We're taking we're going to write two equations about the same problem, and then I'm going to show you how the equations work together to create a solution. So to do this, I don't really have examples for you. We're going to actually use the exercises. So let's go through the exercises to see how this system of equation thing works. Let's start with the exercise on page 295 and see how this works. So I'm going to go straight to page 295 and exercise 1. And it's a problem that you might recognize from other lessons about basketball. It says, Derek scored 30 points in the basketball game he played, and not once did he go to the free throw line. That means, for those of you who are not familiar with basketball, that Derek scored 2-point shots and 3-point shots only, no 1-point shots. List as many combinations of 2- and 3-pointers as you can that would total 30 points. So we need to make his 2-pointers and his 3-pointers always equal 30 points. 2-pointers and 3-pointers all together equal 30 points. Now, this might look familiar. We've done this kind of thing before. Now, you know the 2-pointers, his number of 2-pointers get multiplied by 2. So every 2-pointer he makes gets multiplied by 2 to find his points. The 3-pointers get multiplied by 3. The 3-pointers get multiplied by 3. And we add the 2-pointers and the 3-pointers together to get his total points. So what can he do? What are the different possibilities? Now, you might remember some of these possibilities from before. You might not remember them from before. But let's just talk about like the first case. We need to make 30. Well, I can make 30 all by itself with 10 3-pointers because 10 times 3 makes 30. But if he makes all 30 points with 3-pointers, that means he had 0 2-pointers. See how that works? 10 3-pointers means 0 2-pointers because 10 times 3 makes 30. So you might be saying, well, Mr. Bear, then how about we do 9 3-pointers? Because 9 times 3 makes 27. Problem is 30 minus 27 is 3, and we cannot make 2-pointers to make 3 points. So what we actually have to do is we have to go down. We need to make an even number. So we can't do 9. We have to do 8 times 3. 8 times 3. 8 3-pointers times 3 means 24 points with 3-pointers, which means if he had 24 points with 3s, that gives him 6 points left over, which means 3 2-pointers. Because 3 times 2 is 6, 8 times 3 is 24, 6 and 24 make 30. Again, we cannot do 7 because 7 times 3 is 21, and that leaves 9 left over, and 9 is not even. We need something even. But we can drop down to 6 times 3. 6 times 3 is 18. So that gives us 12 points left over because 30 minus 18 is 12. So he would need 6 2-pointers. 6 times 2 is 12. 6 times 3 is 18. 12 and 18 make 30. You might even see a pattern going here. We're going down 2 on this side and up 3 on this side. It actually continues because we can do 4 3-pointers. That makes 12 points. And he would need 9 2-pointers. 9 2-pointers means 18 points. 4 3-pointers means 12 points. 18 and 12 make 30. He can do 2 3-pointers and get 6 points on this side. If he gets 6 points on this side, he needs to make 24 on this side, which is 12 times 2. 12 times 2, 24. 2 times 3 is 6. 24 and 6 make 30. Finally, he could do 0 3-pointers, and all of the points come from 2-pointers. Well, how do 2-pointers turn into 30? He would need to make 15 of them. So you can see these are the different combinations of how he gets to 30 points with 2-pointers and 3-pointers only. Now we're supposed to write an equation for this. Well, to write an equation for this, we need variables. So I'm going to call the number of 2-pointers x and the number of 3-pointers y. So in this, what did we do to work on this equation? Well, if you look at this, how did we make 30s? What did we do to x and y to make 30? Well, if you look, we did x times 2 plus y times 3 to make 30. This rule follows all of these rows, or I should say all of these rows follow this rule. X times 2 plus y times 3 equals 30. That is the equation we used for any piece of data. So I'm actually going to write that. I'm going to write that in standard form. 2x plus 3y equals 30. And that is an equation for Derek's points. That is one equation for Derek's points. Now keep that page because that is one equation for Derek's points. We're going to learn another fact about Derek's game on page 296. So keep 295 because this gives us one equation for Derek's game. On page 296, exercise 2, we find out that Derek tells you the number of 2-point shots he made is 5 more than the number of 3-point shots. So his number of 2-point shots is 5 more than the number of three-point shots. Well, this means that it's 5 more than three-pointers. So if he makes one three-pointer, we need to do +5 to find his two-pointers. So one three-pointer means he had 6 two-pointers, because this is 5 more, because it says two-pointers is 5 more than three-pointers. If he had 2 three-pointers, we need to do +5. And we're going to do +5 for all of these because he tells us right in the question that two-pointers is 5 more than three-pointers. Two-pointers equals 5 more than three-pointers. So if he does 2 three-pointers, that means he has to do 7 two-pointers. If he does 3 three-pointers, 3 + 5 means 8 two-pointers. 4 three-pointers means he had to make 9 two-pointers. 5 three-pointers means he made 10 two-pointers. 6 three-pointers means he made 11 two-pointers. And this follows the rule he said, because 2 points is 5 more than 3 points. And they also want to have us write an equation for this. Well, for this one, I'm going to say 2-pointers shots are X, 3-point shots are Y. And that follows the same rule we did on page 295, where I said X is 2-pointers and Y is 3-pointers. So the variables mean the same thing. That's important. So we have X equals 3-pointers and +5. X is the 3-pointers +5. It says that in the equation. 2-point shots, X is 5 plus 3-pointers Y. X is 5 plus Y. So that's the equation we have. The equation we have is X equals Y plus 5. So that's the equation we have. Now we have one equation from Derek's game that we did on 295. We have another equation from Derek's game, and both of them are true because they're both based on the facts Derek told us. These equations make a system. These equations today make a system. So to write this system, we can say our system is, we use a bracket like that when we have a system of equations. So we take our first equation from page 295, which was 2x plus 3y equals 30. And we take the other equation, x equals y plus 5. This is our system. System of equations. And I know it's a system because of this bracket. That bracket tells me this is a system of equations. They are both connected to Derek's game. So now we need to figure out what the solution is. And it's actually probably somewhere already on our pages, because this chart is true, and the chart on page 295 is also true. Which of them have the same? Which of them match? Well, if you look at both charts, and let me try to get both charts on the screen right here. There we go. Where do you see the match? Where do you see what is true for both equations? Because let me do the equation 1 is right here. Equation 2's chart is right here. What has the same 2-pointers and 3-pointers? Where do you see that? Hopefully you notice that right here. We have 9 2-pointers, 4 3-pointers right here. And we have 9 2-pointers, 4 3-pointers right there. That is the only one that matches. That is the only pair that is in this chart and this chart. It is the only one. It is the only one that is in both charts. which means it's the only one there. That is the solution. So it is the only one. So that is our solution. So if we want our solution, we say Derek really had 9 2-pointers. I should say 2-pointers and 4 3-pointers. That has to be it, because those are the only numbers that work in both equations, that work on both charts. And the way we write this, because 2-pointers were X and 3-pointers were Y, we do 9 for X and 4 for Y. That is our solution to Derek's game. So we know we took one fact that Derek told us, that he scored 30 points. We took another fact that the 2-pointers were 5 more than the 3-pointers. And those two facts helped us find out what he did in the game. We found out that he did 9 2-pointers, 4 3-pointers. That makes everything true. That is the solution to this system. So we used what Derek told us to make a system, and we compared the two to find the true solution. We found the true solution. Let's do another example. This time we're going to be talking about a road trip and a couple of people who are driving on this road trip. So let's go to Efren and Fernie. Efren and Fernie in exercise 4 on the bottom of page 96. It says, Efren and Fernie are on a road trip. Each of them drives at a constant speed. And there's that constant speed. That tells us it's a linear equation. We need to see that constant speed to know it's linear. Efren is a safe driver and travels 45 miles per hour. 45 miles per hour for the entire trip. Fernie is not such a safe driver. He drives 70 miles per hour throughout the trip. So Efren is 45 miles per hour. Fernie is 70. Fernie and Efren left from the same location, but Efren left at 8 a.m. Fernie left at 11 a.m. Assuming they take the same route, will Fernie ever catch up to Efren? So Fernie left later. He left 3 hours later. He left at 11 instead of 8. But Fernie also drives faster. So Fernie left later, but he drives faster. So the question is, will he catch up? Will they meet? And if they will meet, when? So this is a common type of problem where you try to figure out if you will ever meet your friend. Like maybe you make plans, you know how you each drive. Maybe you want to meet for lunch later. This will tell you if it's possible. So part A, write the linear equation that will represent Efren's constant speed. Make sure you include in your equation the extra time that Efren was able to travel. So Efren, remember, was 45 miles per hour. So y, Efren's distance, equals 45 miles times hours. So if he drives for 1 hour, that's 45 times 1. He goes over 45 miles. If he drives for 2 hours, that's 45 times 2. That makes him go 90 miles per hour. But it's not just 45 times x, because he also started 1 hour later. So he started 3 hours earlier. He started at 8. Fernie left at 11. So Efren gets 3 extra hours. So he gets the X hours he's driving. He gets the X hours he's driving plus 3 extra. He gets 45 plus 3. He gets X hours plus the 3 extra because he left early. So let me write that a little bit clearer. And let me write it in red because I said Efren was red. Efren is 45 miles times X hours plus 3 more because he left early. So he left early, so he gets 3 miles. And then write a linear equation for Fernie's constant speed. Well, Fernie is just y equals 70x. Because Fernie did not get any extra time, we don't change x. Fernie is just y equals 70x. So that is Efren's equation, that is Fernie's equation, with the extra time that Efren got, but with Fernie's faster speed. Let's look at 4C and see what they want us to do with these two equations. Okay, so they say write the system of linear equations. So this means we need to write a system. Now remember, when you write a system, you use that fancy bracket right there. So that tells you, this bracket tells you it's a system. So you write both equations in that system. Both equations in that system, just like that. There you go. That's what the both equations look like. You can even, if you want, because you can look at part D and see they're going to want to graph this, you can even change the system to make sure that Efren's is in slope-intercept form by using the distributive property. 45 times x is 45x plus 45 times 3, which is 135. Same way, except for this makes it, this is a little bit easier to graph. It's easier to graph this because it's in slope-intercept form. So it makes it easier to graph, but it means the same thing. We just use the distributive property to change it. Because in part D, they do want us to graph it. So let's graph both these equations. I'm going to start with Efren's just because it's on top. We follow the slope-intercept rule. So we know for Efren, we need B. Let me do Efren. We need B, and we need M. Well, Efren's B is 135. That's because he got a head start. His M is 45, which means 45 over 1, which means up 45, right 1. So that's the information we can use to graph Efren. Let's also get our information for Fernie. We need Fernie's y-intercept, and we need Fernie's slope. Now, Fernie is just 70x. There is no B, so B is 0. But his slope is 70, which is 70 over 1, which means Fernie goes up 70, right 1. Sorry, I should put these y-intercepts in coordinate form, 0, 135. And we could use these equations. We can use y-intercept and slope for Efren, y-intercept and slope for Fernie to graph them. So let's do that. Let's see. Let's do Efren. His y-intercept is 0, 135. So 0, there's 100, there's 150. It's going to be about right there. That's his y-intercept. Now he goes up 45, right 1. Well, 135 plus 45 is 180. So we need to go about 180, which is right here. That's going up 45, right 1. So his point is going to be right there. For Fernie, his y-intercept is 0, so his first point is right there. And we follow his slope rule, up 70, right 1, which is going to be probably about right there to go up 70. Then he goes right 1, so we're going to look about right there. So now we have their slope, we have their intercepts, we follow the slope rule. Now what we need to do is we need to connect those 2 points so that we can see what their lines look like. There. So let's connect these 2 points to see what their lines look like. So we'll do Efren's line first. So that's it, what happens if we connect Efren. So I'm going to label that with an E. And then for Fernie, let's connect it right there. That looks like it's about right. Okay, so there we go. It looks like they do hit. Fernie's line does cross Efren's line. So part E, will Fernie ever catch up to Efren? Yes, Fernie will. We say Yes, the lines do meet up here. When? How many hours? Well, it looks like it is about, it says approximately, so I'm going to say about. And also because the intervals were we kind of guessed at the intervals where like 135 and was and where 75 was and those kinds of things. The intervals were kind of in the middle, so I'm going to say approximately. It looks like 6 hours. I'm guessing close to 6 hours. Maybe we'll say we'll say about 6 hours. So about 6 hours after Fernie starts driving, because Fernie was the 0. Fernie hit 0, so it hit 6 hours after Fernie. Fernie left at 11 a.m., so I'm going to say about 6 hours after Fernie leaves, which is about, he left at 11, so about 5 p.m. About 5 p.m. And at approximately what point do they meet? I'm going to say that is going to be the point. The coordinates are, it's about 6 on the x, and it looks like it's about 400 on the y. So I'm going to say they meet at 6, 400 about. That is probably about where it is. That's about where the lines cross. So I'm going to say Fernie catches up after he drives for 6 hours. If he drives for 6 hours, he should catch Efren because he drives faster, and he makes up Efren's head start. So about 6 hours or 400 miles is when I'm guessing, I'm approximating, not really a guess, it's an approximate because I did graph and I did do math. So I'm approximating about 6 hours or 400 miles. There is a way to find it exactly, which we'll work on another lesson. Right now, I just want you to be using graphs to solve these, but we will talk later about how to find it exactly. Right now, you're just going to graph and get approximate answers. That's why I said about, because we're just doing approximate today. There is a way to find it precisely, exactly, and we will talk about that. So if you're a perfectionist who needs to know the exact answer and our graph is not perfect enough for you, just wait for a future lesson and I'll show you how to find it exactly. But let's do another example. Let's go to page 298 and we'll talk about Jessica and Carl. And I believe Jessica and Carl are our last exercise that we'll talk about. So Jessica and Carl. Jessica and Carl run at constant speeds. So we'll do Jessica and Carl. And good news, they run at constant speeds, which means we can do linear equations for this. Jessica can run 3 miles in 24 minutes. Carl can run 2 miles in 14 minutes. They decide to race each other. As soon as the race begins, Carl trips and takes 2 minutes to recover. 2 minutes to recover. So that means Jessica gets 2 extra minutes because Carl is on the floor crying because he tripped. And so Jessica gets 2 extra minutes. So let's write the linear equation that represents Jessica's constant speed. Part A, let's do Jessica's speed. So we know Jessica does 3 miles in 24 minutes. So if you're going to write this linear equation, remember you could do 3 miles in 24 minutes equals y over x to make this into a linear equation, because you take what you know and what you want to know. So you get, if you do that, you get 3x equals 24y. You divide by 24, you get y equals 3 over 24x, which 3 over 24 simplifies to 1/8 x. So Jessica's speed is y equals 1/8 x. But remember, she got those 2 extra minutes. So we have to change her x. So Jessica is actually 1/8 times x plus 2, 2 extra minutes. So this is Jessica's speed. This is Jessica's speed with the extra 2 minutes. Now, part B, let's do Carl's speed. Now, Carl does not get extra time, so we can just do Carl is 2 miles in 14 minutes and use our proportion to find his speed. So he gets 2/14 x, which simplifies to 1/7. So Carl's speed is y equals 1/7 x. So now we have Jessica's speed with the extra time and Carl's speed with no extra time. Write the system of equations. Now, write the system of equations. Remember, the way we write a system of equations is we use this fancy bracket and we put both equations inside the bracket. So we take Jessica's equation, and I'm going to just use the distributive property, multiply 1/8 by both. I get 1/8 x. 1/8 times x is 1/8 x, plus 1/8 times 2 is 2/8, which is 1/4. So this pink and this pink are the same thing. It's just after this distributive property. Why did I distribute? So that I did it so that I have slope-intercept form, make it easier to graph. Carl's, I don't have to use the distributive property. It is already in slope-intercept form, so I can just leave it like that. That's my system of equations right there, with Jessica's equation and Carl's equation. So let's sketch the graph to see if when Carl will actually catch up, because Carl does go a little bit faster. He can do, if we look at the unit rate, Jessica can do 1 mile in 8 minutes. Carl does 1 mile in 7 minutes. So let's see if Carl will catch up because he goes a little bit faster. So we're going to sketch. Now, when we sketch again, remember we have Jessica and we have Carl. And to graph these, we need to know slope-intercept form. M and B, the intercept and the slope for both of them. So Jessica's y-intercept is 1/4, which means it is 0, 1/4. That's where it crosses the y-axis. And Jessica's slope is 1/8, which means she goes up 1 and right 8. Carl's y-intercept, there's nothing there, which means his y-intercept is 0. So he crosses the x-axis at 0, the y-axis at 0, 0. But his slope is 1/7, which means he moves up 1, right 7. So that's the information. Let's use that information to graph these lines. Jessica, let's see, we can see all the graph now. Good. Jessica starts at 0, 1/4. That's the point. First point. So 1/4 is 0.25, which is going to be about right there. That's where she starts. Now she goes up 1, right 8. So 0.25 plus 1 is 1.25. Remember, we're adding 1, up 1. So we add 1, 1.25. And we go right 8, which is right here. So 1.25 right 8, which means she's looking at about right there. So that's the y-intercept, and we follow the slope rule, up 1, right 8. So if we graph Jessica's race, this is approximately the points of Jessica's race. We did kind of have to guess a little bit because where 0.25 was. Now let's worry about Carl. Now Carl crosses at 0, 0. So that's his y-intercept. And now we follow his slope rule, which is up 1, right 7. So up 1, we go to 1, because that's 1. We don't go up 1 box. We go up 1. And then we go right 7, which means his second shot is right there. His second point is right there. So they do cross, it looks like. Looks like they do cross. They cross about right here. They cross about right there. That is where they meet on the racetrack, and that's where Carl starts to win. So let's see what question E is like. Use the graph to answer the questions. If Jessica and Carl race for 3 miles, who would win? Who would win if they race for 3 miles? Well, remember on this one, Y was the miles. So if they race for 3 miles, means if they race like this is time, X is time, and I don't like how they did not label that for you, but X, remember, is time, Y is miles. If they race for 3 miles, you can see if we go to the 3-mile mark, Carl will be there before her. Carl's graph will hit the 3-mile mark before Jessica's graph. We cannot see the 3-mile on here, but we know that Carl will hit 3 before Jessica hits 3. So if they race for 3 miles, who would win? We will say Carl will win because his line gets to 3 miles before Jessica's line. Good. We can see that in the graph. Carl's line will get to 3 before Jessica's line. At approximately what point would Jessica and Carl be tied? Okay, well, that's this right here. And we just need approximate, so I'm just going to say it looks like about 6 minutes, 6 on the X, and about 0.8 on the Y. So I'm going to say about 6 and 0.8. That's approximately. That's close. And remember, our Jessica's graph is not perfect, so I'm guessing that's about where it is. Remember, it's just saying approximately, so our answers can be a little bit different if your graph looks a little different than mine. But that's about where it will be. And explain, how do I know this? That's the point, because that is approximately where their lines cross. Or I'm going to say intersect, because that's a better math word than cross. So you can see how these systems of equations, how finding the equations, writing them in a system, and graphing them can help us find answers. We can find out who's going to win races. We're going to find out who drives faster and when they'll meet. We can even solve questions about basketball games. So that's what the value of these systems of equations and graphing them. You're going to practice this independently a little bit. So let's keep looking. Turn the page, and there's your lesson summary that we've talked about. It tells you the definition of a system of equations, tells you the definition of a solution to a system of equations, gives you what a system of equations looks like using the brackets. So there you go. It shows you the brackets. All 3 things we talked about in today's lesson. On the next page, page 301, is your exit ticket. It's actually pages 301 and 302 are your exit ticket. So you're going to work on both those, but we're going to work on them at the end. So let's talk about them last. Page 303, and I believe there's a few more pages, 303, 304 are both your homework helper. If you need more advice, more examples, homework helper is great because it gives you another problem, tells you the answers, and tells you what you should be thinking. But that's on page 303 and 304. Page 305 and 306 is your problem set, where you're going to practice these a little bit on your own. A couple more problems where we're talking about rates and equations and systems of equations and graphing them to solve them. Work on them, do your best, but remember my answers to the problem set are online, so you can look at those and you can look at my answers, check your answers with mine to make sure you know what you're doing. And remember, always ask me questions if you get stuck or need more help on something. So your problem set on pages 305, 306. After you check your answers to those and you know what you're doing and you feel confident, Then you can work on the exit ticket, go back to the exit ticket from 301 and 302. And there's a question about Darnell and Hector riding their bikes. You're going to be doing the same thing. The whole exit ticket is just the question about Darnell and Hector riding their bikes. You're going to write Darnell's equation, write Hector's equation, write the system, make the graph, and then answer questions by looking at the graph. That's what you're doing today. Remember, when you're done with the exit ticket, to take a picture of it and turn it into the Google Classroom so that I have evidence that you did what you're supposed to do. And that's it. That's what you're doing today. Writing some equations, turning them into a system of equations, graphing, and answering questions. I know you can do this. We've done a lot of this before, just kind of putting different ideas together into something new. Work hard, do your best, don't give up, persevere, and I will see you for the next lesson.